Gartner predicts that over 40% of agentic AI projects will be canceled by the end of 2027. These failures aren't typically caused by weak reasoning models, but by costs and risk controls that spiral as memory architectures degrade in production. The standard practice is to supply frozen large language models with large volumes of passive semantic data. Over time, this static context causes the agent's logic to drift, leading to hallucinations and a loss of foundational capabilities, a process known as catastrophic forgetting. Welcome back. I'm here to translate the theories of the human architect into actionable blueprints. Today, we are mapping a runtime learning stack designed for the technical and regulatory requirements of 2026. The catalyst for this architecture is MemRL. This research provides evidence that to solve long-term degradation, we must decouple the reasoning backbone from memory storage. In production, standard retrieval augmented generation, which pulls data based on simple keyword similarity, is no longer sufficient. To survive, developers must treat memory retrieval as a reinforcement learning policy, optimized by environment feedback and asynchronous updates. This dual-stack approach allows systems to accumulate intelligence through experience without destabilizing the underlying model. Every learning AI faces the stability-plasticity dilemma, the trade-off between retaining established logic and acquiring new information. If you prioritize plasticity by frequently updating the model's weights with new data, you risk overwriting foundational logic. The model literally forgets the basic tasks. On the other hand, if you prioritize stability and lock the model entirely, the agent becomes rigid. It cannot adapt to its environment. MemRL addresses this by keeping the backbone LLM completely frozen. This ensures that the agent's core reasoning remains stable and predictable across every session. Adaptation is moved to an external, mutable, episodic memory bank. This allows the system to remain plastic, changing and improving over time, without ever modifying. Freezing the reasoning engine while keeping the memory bank fluid provides the structural baseline for a self-improving agent. Standard RAG pipelines struggle because they rely on cosine similarity. This mathematical lookup often retrieves semantic distractors, data that sounds relevant to the query, but MemRL replaces this lookup with a Markov Decision Process. In this framework, memory retrieval is treated as a decision intended to maximize the agent's success. To make this work, MemRL organizes stored memory into a strict three-part structure. First is the intent, which stores the vector embedding of the specific task or query. Second is the experience, containing the summarized trajectory or the specific steps taken to solve that task. Finally, the utility layer stores a learned Q value. This signals whether this memory historically helped the agent succeed or led it into an error. Retrieval follows a two-phase process. First, a standard coarse semantic filter generates a short list of possible memory candidates. Then, the system applies the learned Q values to that shortlist, actively filtering out the distractors that have a high probability of leading to failure. Implementation details show that a Q-weight balance of 0.5 effectively blends semantic similarity with this historical utility signal. Memory retrieval is no longer a passive search. It is an active decision process that learns to suppress misleading information over time. We can see the impact of this filtering in the ALFWorld benchmark, which tests an agent's ability to navigate multi-step domestic tasks. Using a controlled GPT-4o mini backbone for the tests, the researchers isolated the effectiveness of the memory policy from the raw power of the underlying model. Without any memory assistance, the model achieved a success rate of only 0.278. When the MemRL policy is active on the same model, the success rate reaches 0.440, an improvement of roughly 58%. This edge comes directly from reinforcement learning-driven filtering. By suppressing noisy or misleading memories, the agent avoids the regressions that typically plague multi-step environments. The result is an agent that consistently improves its practical success rate by refining which experiences it chooses to trust. While MemRL adapts memory selection, there are moments where you may still need to update the model's core reasoning. This requires a complementary approach. AReaL serves as the infrastructural lever for systems that need more than just memory updates. AReaL is an open-source, fully asynchronous reinforcement learning training system designed for large reasoning and agentic models. It is designed to make training time weight updates practical at scale, allowing models to be refined without taking the agent offline. AReaL integrates via an OpenAI-compatible proxy. This allows developers to connect existing agent workflows, built-in LangChain or Camel AI, directly to the training system. Connecting an agent requires minimal code changes. Developers simply point their standard SDK clients to the AReaL proxy address. The heavy lifting is handled by the Archon engine, which uses 5D parallel training to manage high-throughput updates across reasoning models without disrupting the agent's performance. By combining MemRL's post-deployment memory adaptation with AReaL's asynchronous weight updates, we can build a complete self-evolving loop. This shift toward runtime learning is driven by the reality of model drift. Even the most capable models change their behavior over time, which can break critical production workflows. Research comparing snapshots of GPT-4 shows that its ability to identify prime numbers dropped from 84% to 51% in just 3 months. When the underlying model drifts like this, an agent's performance can collapse without any change to its own code. There is also a legal mandate for self-monitoring systems, the European Union AI Act. Article 15.4 of the Act specifically requires providers of high-risk self-learning AI systems to mitigate the risks of feedback loops, where biased or incorrect outputs become training data for future operations. The timeline is concrete. The AI Act became law in 2024 and will be fully applicable by August 2, 2026. The deployable stack is now taking shape: a frozen LLM for logic, Q-value filtered memory for adaptation, and an asynchronous AReaL proxy for structural training, all supported by a mandatory monitoring plan. Designing for continuous adaptation is becoming both a technical and a legal requirement. By building the architecture for runtime learning today, we enable agents to safely and effectively teach themselves.